Hey everyone, so this is Dr. Sergey Sarkisov, and today we're going to look into some of the sum and difference of angle formulas and actually extend it further. So let me write that as, this is class of trigonometry, right? And we're going to talk about angle formulas today. And you'll see how these results that we get today can be applied in numerous ways in trigonometry and in further applications, engineering, science, whatnot. Okay, so first, let me, and I'm going to do a geometric, not algebraic, but more of a geometric proof. There are other ways of a very interesting and important result in mathematics. So watch this. Let's say we have two angles. So for instance, let's say you have an angle, and an angle is what? You have a vertex and two rays coming out of it, right? So here's a vertex, wherever that point is, right? And there's a ray, let's say, going somewhere. And here's a ray. And the measure of that angle, that angle size, the measure of that angle is, let's call it angle alpha. Okay? And then let's say somebody tells me, well, I'm giving another angle, beta, another arbitrary angle. And I'm going to allocate it so that this is going to be my vertex, and one of the rays is going to be, let's say, this one. So the other one will have to make this beta. Say that's beta, right? And that's the measure of that new angle. So let's just draw another ray. And so these are two arbitrary angles. I really didn't do anything to, like, this is not like necessarily 20 degrees and 30 degrees, nothing like that. It could be any two angles, okay? Now what I'm going to do is, I'm going to pick a point. I'm going to fix a point right up here. Okay? That's okay, right? It's still arbitrary, not changing anything, not making anything too specific. And I'm going to draw a perpendicular through this point to this line here, this middle one, this middle ray. So let's do that. And then all these intersections here, we'll have them labeled as also other vertices, but that's going to be perpendicular. That's a 90-degree angle between this ray and this line segment. So now we're going to look into this triangle here, these three vertices here formed, and the two triangles inside of that big triangle. Okay. So watch this. Let's label these sides as, call this, for example, M. From here to here, the length of that line segment, and this line segment, call this length N, okay? And then, you know, why not, let's call this side angle, the length L, and length, let's see, let's do something like L, and then O, P, length P, and length Q. So three lengths, whatever they are, right? And what we're going to do is, we're going to use areas of the triangle somehow. So what do I mean by that? First, let's recall this result that we've studied a little bit earlier in our class. Okay? And so what this is as follows. If I have any triangle, right? First I'll have a rectangle. What does it mean area? Let's go back to the basics. What does it mean area? It means how many unit squares do I have inside that rectangle. In other words, if I have a 3 by 5, or let's say 4, right, by 2, 3, 4, 4 by 6 rectangle, okay? You see, what does it mean 4 by 6? 4 rows of 6 columns. And when you say the word of, you multiply. The area would be 4 times 6. In other words, if I have a width, let's call this actually height, and this is a base. So base times height, or width times length. The area of this rectangle will be what? H times B, right? And what happens when you have a triangle, you always can circumscribe it or go around it with a what? With a rectangle. In other words, here's a triangle. We want to do the area of a triangle is what I'm trying to show you. So let's say I have any triangle like this, and what I'm going to do is, if this is my height H, and this is my base B, now this makes more sense for a triangle, right? How do I know the area of this triangle is equal to, and we kind of are used to that formula, 1/2 base times height, 1/2 base times height. We're told that so much, but why is that the case? And this is because we actually have around it, we can make it a rectangle. And if you see, then this area will be that one, right? And this area will be this one. So it is 1/2 of the area of the rectangle around it, and that is why it's 1/2 of the h times the b. 1/2, or let's write base times height. Okay? And so that's still not going to help us. We still need some other, and then you'll see what we do with this new result. But watch this. Another thing we can do is, let's say we have a triangle, something like this, some scalene or any isosceles, equilateral triangle, anything, any sides, any angles for a triangle. Let's call this vertex B, call this triangle A, B, C. So in other words, length B here, right, little b opposite the angle B. Opposite vertex A, or angle A, we're going to have little a side length, and then C here. And what I'm going to do is, I'm going to draw, so let's say we know A, B, and C, and maybe this angle, call this angle theta, okay? And that's it. So basically, I know A, B, and the angle theta, and maybe C also, but look, I don't know the height, and so I draw the height, call it H, right? Call it H, this is a perpendicular here. A little altitude drawn to the base, okay? And how do I find the area of the triangle? Well, the same thing, we can say, okay, area of the triangle, right? And this is nothing trigonometry yet, no sine, cosine, tangent. The area of this triangle is equal to, again, the same thing, 1/2 base, right, times the height. But what is my height? So look at this, the height, right? The height is what? The height over the A, which is the hypotenuse of this triangle. There's a right triangle here, the small one. That's h over A. That's opposite over hypotenuse for the right triangle. Is sine of the angle theta. That's what it means, sine, right? By definition of the right triangle, trigonometric definitions of the functions. What does it mean, sine of theta, or sine of the angle C? It means exactly for a right triangle, h over A. If we're talking about specifically this triangle. So now look, what is my h? Well, solve for h, you get A sine theta. And we plug this here into this h, and we get 1/2 b, and then A sine theta instead of h, or substitute, right? And that's going to be, if I write it in kind of alphabetical order more so, 1/2 AB sine theta. And what I always tell my students is, kind of the visual, I'm saying, okay, look, we have sides here, two sides here, like this, and the angle between them. So 1/2 area is going to be 1/2 side multiply, right? The length times the sine of the angle between them. 1/2 sine angle between them. Try to remember that, because now what we're going to do is we're going to look into this triangle more further on, right? And so let's see what we can do here. What is my area? Let's call this area of triangle 1. And let's call this area of triangle 2, this other right triangle. So how do I find area of triangle 1? Oh well, let's try this. Area of triangle 1, right, is equal to, now look at this. Where do I get an angle? I know angle alpha, right? And so what else do I know? I know the lengths L and P here, side length. So look, I can say, okay, it's 1/2 L, right, P, sine of the angle between them, which is alpha. This comes from that, that result that we talked about there, right? What about A2? Very similarly, it's going to equal to 1/2, but now what? This sine angle beta, right? So 1/2 QP, P, and then sine angle beta. Okay? Well, why am I doing all this? I'm going to say one more thing. What about the area of the whole triangle? A1 plus A2. In other words, area of the entire triangle is the big one, right? Which is A1 plus A2. But what is the area of that big triangle? It's going to be LQ sine of that whole angle there. 1/2 LQ sine of the angle alpha plus beta. And that's the first time we're seeing sine of sum of angles alpha plus beta. So this is going to equal to 1/2. What is that? LQ, right? Two sides and then the angle between them, which is alpha plus beta. And that's where we're introducing this sine of, look at that, alpha plus beta. But we didn't find any formula for it. We just are right now expressing it, at least in to help, using it to express the area. of this entire triangle. Now what I can do further, let's erase this, what I can further do is, well, I have area 1 plus area 2 is equal to the whole area. We haven't said area 1 plus area 2. So let's write that as, but let's write the expressions for those areas, right? The other ways that we have written it. So 1/2 LP sine of alpha, right? That's area 1 plus area 2, right? The second triangle area is 1/2 what? QB sine beta, okay? And that is all equal to the area of the whole triangle, right? 1/2 L Q sine of the angles, the sum of the angles alpha plus beta. All right, well, this is interesting. We're getting some kind of alpha plus beta in terms of all this other, right? All these variables and parameters and expressions. So what we can do now is let's simplify this further. I don't like the 1/2 everywhere. I can cancel it all out, right? Divide both sides of the equation by 1/2. I can get rid of the L's some places and Q's and P's. Let me divide everything by 1/2 L P Q. 1/2 L P Q and 1/2 L P Q. And what I'm left with, if you look at that further, 1/2's cancel, LP cancel, so it's going to be what? It's going to be sine of alpha. One second, something. Let's see if everything's making sense here. So, did I have anything left out? Oh, so 1/2's cancel, right? So we have. Let's see. Let's try to do this as. So, this is true, right? But what am I missing? Let's continue with this, and you'll see how we can kind of come up with something what the issue is. So I'm trying to show you something. So 1/2 L, 1/2 L goes away, P goes away, right? And you have Q at the bottom there, right? And then that's what? Let's see. Let's do this. 1/2. Oh, let's try this. Here's a better way to look at that. So let me divide everything with 1/2 LQ. Okay, you see what I'm doing? I'm trying to isolate the sine alpha plus beta. That's probably more what would help us. So let's just divide by 1/2 LQ, 1/2 LQ, and 1/2 LQ, right? And now we're going to be left with a P there, seemingly unfortunate for us, but at the same time, it's going to be pretty nice. Watch. So 1/2 L, 1/2 L go away. 1/2 here, and then the Q's go away, and then this whole expression goes away. And so we are left with sine of alpha plus beta, okay, is equal to, right? What is P over Q? P over Q, before I tell you sine alpha, right? Sine alpha times P over Q, okay? And I'm going to rotate sine alpha to this, right? Commutative property of multiplication. So sine alpha times P over Q, or P over Q times sine alpha. You can flip those around in that order. So sine alpha times, what's my P over Q? What is that P over Q? It's going to be, let's see, P over Q. For this triangle, that's adjacent over hypotenuse. That's cosine of beta. So cosine of beta, right? That's a nice way to write that just in terms of angles. And what about this one? Well, if you have P over L left, what's P over L? P over L, the adjacent over hypotenuse for the alpha right triangle, first right triangle, and that's alpha. So cosine of alpha now, okay? And let's leave it here. So this is cosine of alpha, and then of course sine beta was left there, right? And when you see this, this is called the sum of angles formula. Okay, the first one, and actually the one that will get us a lot of results. So this is a big formula. Sine alpha cosine beta plus cosine alpha sine beta. That's what sine alpha plus beta is equal to. What is this all? How could this be used in any form or fashion? Watch. Let's first use something we already know. Let's use angles we know everything for, just to kind of to do nothing new besides to test. Is this really probably going to work every time? So look, let me erase this for a moment, and we will try some angles. Let me show you. For example, what if we tried 30 degrees, 60 degrees, and 90 degrees? What I mean by that is, here's an example. That's the first example. This is kind of redundant. We don't need to do this. This is not. If you had done, and we're doing this only for what I'm about to do, you'd never need to do this. You'd never have to find this formula. But let's say I told you what's sine of 90 degrees, and everyone knows this is 1 on the unit circle, right? It goes up, maximum 1 for the y value for the sine. So we know it's 1, but let's say we didn't know that, but we knew it's also sine of what? What's 90 degrees? It's 30 degrees plus what? Let's make it easy angles. So instead of me doing like 1 degree and 89 degrees, let's do 30 degrees and 60 degrees. I know everything about those angles. Okay, well that's sine of, like, we'll call it alpha plus beta for a moment. What is that equal to? By this formula, it's sine of alpha, which is 30 degrees, cosine of beta, which is 60 degrees, and then plus a cosine of alpha, right? Cosine of 30 degrees, and then a sine of that other angle, 60 degrees, the beta. And let's say I knew this. Now I'm going to use these before I even say that's a 1. Let's see, is this actually going to give me a 1? And so that's a what? That's a 1/2. You know, the sine of 30 is 1/2 degrees. Cosine of 60 degrees, that's also 1/2, right? And then cosine of 30, that's a √3/2. And sine of 60 is also √3/2. Okay, let's see if that is equal to, right? Is it going to give me a 1? Like, I know this is a 1, right? So, let's see. 1/4 here plus a square root of 3, making a 3. On the top, 3/4, and that's exactly a 1, right? Check mark. That's what we wanted, that 1, sine of 90 degrees. Again, nothing new besides I'm using this formula somehow, and it's kind of making sense, right? Let me show you another, more important way to use this formula. For what example would I want to use this formula? So let's call this another example. Okay. And let's try the following. Let's say you're asked, what is the sine of 75 degrees? This is not the common angle for us. This is not 30 or 0 or 45 or 60 or 90, right? It's a reference angle, but that's all we know. It's a reference angle, and it's also the sum of two angles we can use. What are they? Let's try 30 degrees and 45 degrees. I know those angles very well. Those are common angles. And so let's say, instead of, because I don't know what this is equal to. We have not done that before. And now, let's say it's sine of what? Let's try 30 degrees plus a 45 degrees, right? And then I'm going to do the same concept here. I'm going to use that same formula, sine alpha, cosine beta, plus cosine alpha, sine beta, right? And let's see what that gives us. I know all of those expressions right away. So look, it's going to be sine 30, cosine 45, right? And then plus, now cosine 30, and what? Sine 45 degrees, right? The beta. And so that's equal to, let's see what that's equal to. That is equal to 1/2 here, sine 30, and cosine 45 degrees is what? That's a √2/2. So it's 1/2 times the square root of 2/2, and then plus, that's going to be cosine 30 is a square root of 3/2, right? And then times sine of 45 is also square root of 2/2, just like cosine 45 was. And that's equal to, look, square root of 2/4 plus a square root of 6/4, right? Square root of 2 and square root of 3 multiplied together gives you a square root of 6. And that's going to be, if you put it all over, making a common fraction, all over 4, a bunch of fourths, it's all right, common denominator here. Square root of 2 plus a square root of 6. And that's an interesting result. We never saw that before. And you can check on the calculator, like try the number square root of 2 plus square root of 6/4, and then directly say sine of 75 degrees. You will get the same answer. It's kind of interesting. You'll see that. Okay. So I said angle formulas, and we have angle formula. That's an important formula, but what about any other formulas? What about, like, what if I said cosine? What if I said sine alpha minus beta? How would I do that? And this is where we're going to do the following. We're going to use this formula each time to get the other formulas. Watch this. I'm going to erase the following, and we are going to first look into what is sine of alpha minus beta. What if I'm subtracting angles? And how am I using that formula So watch this. Let me copy this formula one more time. Erase the board here. And we will have board. So we will have the following. First of all, we know the result that sine of alpha plus beta, okay, is equal to sine alpha cosine beta plus cosine alpha sine beta. Okay. How do I find the sine? So this is a big result here. How do I find sine of alpha minus beta? Well, kind of looks similar, right? It says one's addition, one's subtraction. What if I told you, look, subtracting a number, remember that, it's just adding a negative of it, right? So sine alpha, this is plus a negative beta. So I can use the beta, for beta I can put a negative beta in, that's going to be the same result. And so watch this. It's going to be writing the same formula, but using this same formula. So sine alpha, cosine, now beta is now negative beta, and then plus a cosine alpha, and then sine of what? That negative beta now. And this has to do with odd and even. This uses the result of odd and even functions. If you remember for a moment the following, and I kind of have shown you this way, right? If I have an angle, theta, let's say, and here's a negative theta, right? I go clockwise. If this is my x value, that's cosine of negative theta, and then that's going to be sine of that angle down here, right? And this angle, well, I know that for a unit circle, right? That's a what? That's going to be just always x is the cosine of that angle theta, and that's the sine of that angle theta. And what you can see is cosine, negative theta and cosine theta are equal, right? So cosine of theta, let's say cosine of negative theta, right, is equal to cosine of theta, just because it's an even function. Why? Just because, why? Because this is x value both going to the right, for example. You could also do a bigger angle, you'd have them both going to the left. Anyway, so this is true, and also they're opposite y values, right? So you actually have sine of, this is an odd function, which is what? That if I told you sine of negative theta, you'd tell me negative sine of theta, okay? So how do I use that here? Well, what I'm going to do is, I'm going to put this as sine alpha, and then cosine negative beta is, again, cosine of beta now, right? So just write it as cosine beta. We'll have a negative sign there. We don't want that, right? So we just have cosine beta plus a cosine alpha, and then sine negative beta is going to be a negative sine beta. And so what happens is, overall, we're going to get a sine alpha cosine beta minus, the minus comes out in front here, cosine alpha sine beta. And so what do you see? Very little has changed, besides if you put alpha minus beta, you'll have not a plus sign, but a minus sign. Okay? So this is a big result that we are using here, and this is a big result that we have derived also from the first one. Okay? All right. What other ones are there? How about cosine alpha plus beta? Now that's a different trigonometric function. But if you think about it, cosine and sine are cofunctions. They are the same if you take one of like sine of 90 minus theta, the complementary angle of theta, right? You're going to get cosine of that angle theta. You remember how to relate those sine and cosine together? Watch this. I usually use a right triangle to show you what I mean by that. So watch. All right, just similarly how to do the even and odd. Let's say I have a right triangle, and let's say I have, okay, well here's a theta. That's going to be a right triangle. That's going to be 90 degrees minus theta, right? What happens is, if I tell you, okay, this is for angle theta, right? Let's call this my A, my B, and my C hypotenuse here, right? A, B, and C. C is all its hypotenuse. What is my sine of the angle theta? Well, it's hypotenuse, opposite over hypotenuse, so A over C. Right? And that A over C is adjacent over hypotenuse for this angle. So equals to cosine. Adjacent is over hypotenuse cosine. But of the angle 90 degrees minus theta. And this is cofunction. The cofunction formula. Okay? And you can also do that between tangent and cotangent, or cosecant and secant. But let's use that. So how are we going to use that for our result of the following? Finding cosine, it's another one, so this is put a star here. There's another one, a big one, cosine of alpha plus beta. And there's another way to do this. You can do a algebraic slash coordinate kind of geometric way to do this proof. You could have actually done this one first before ever doing this one. Okay? A lot of books will do that for you. But we've done this again how? We did the sum of areas of a triangle. It was really neat, right? And we found that the area of one triangle is the area of the other is going to be, of course, the area of the whole triangle. And we found this formula ultimately. Well, look at this. Cosine is what? Again, it's cosine of 90 degrees minus theta is sine of theta. And if you do the other way around, right, you'd also get cosine of alpha plus beta is going to be sine of 90 minus that angle, right? So sine of, very similarly, if I put a cosine here, cofunction, so also cosine of theta, try that's going to be b over c, and that's going to be sine of 9 degrees minus theta, right? That angle is sine b over c. For that angle, it's going to be opposite of our hypotenuse here. So we're going to use this one specifically. And we're going to say cosine of an angle is, sine of 90 minus that angle. 90 degrees minus that angle. So 90 degrees minus my alpha plus beta angle. So I went from cosine to sine. Okay. And what is this equal to? Well, it's equal to sine of, let me rewrite it a little bit more neatly here. So watch. How about I say sine of 90 degrees minus alpha, right? And then minus a beta. I'm going to put this in parentheses here, this 90 degrees minus alpha, and put a minus a beta, right? That's the same thing, 90 degrees minus alpha minus beta, 90 degrees minus alpha minus beta. Okay, distribute this negative sign. Now, what I know is, I know this is an angle minus another angle. We've done that, sine of an angle minus another angle. So look, it's equal to sine alpha cosine beta minus cosine alpha sine beta. So sine of the first angle, 90 degrees minus alpha, cosine of the second angle, which is beta, okay? Something minus something called x minus y is going to be sine of x cosine of y minus cosine of the x, okay? Sine of the y, the second angle, okay? And that's equal to, so we have a big result already, right? We're kind of getting there. But and then what is sine 90 degrees minus alpha? We can use that right there, which is cosine of alpha. So it's equal to cosine of alpha times cosine of beta. And then minus, what is cosine of 9 degrees minus alpha? Oh, it's sine of alpha. Sine of alpha. Sine of beta. And that is the formula we're going to leave ourselves with. And we have found the formula for cosine alpha plus beta. And similarly, it's a pretty cool formula, right? If we're gonna, we're looking into, for example, the last one that we haven't done for the sum and difference of angle formulas, right? We can do cosine of alpha minus beta, right? And so that's going to equal to, well, just use a negative beta for a beta, and we can quickly do this as, I'm going to put a little dot, 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 ellipsis. So cosine of alpha, cosine of negative beta, right? And that negative beta, we'll get a cosine of beta still out of it, right? Because remember, we did this is an even function. So cosine of a negative angle is cosine of that positive angle. So we just you get rid of the negative sign soon enough. And then minus sine of alpha, sine of a negative beta. So that sine of negative beta will turn out to be a negative sine beta. So it's actually equal to cosine alpha, cosine beta, minus, and that's a minus that's going to come out, right? Sine of a negative angle is negative sine of that angle. So it's going to be actually not a minus, but a plus sine of alpha, sine of beta. And that is our final result for the sum and difference of angle formulas that we want for sine and cosine. Okay. What more? You know what more? How about the double angle formulas? Anyone heard of that? Like what's sine of 2 theta? What about cosine of 2 theta, right? What about half angle formulas? So those are really neat. And I encourage you, I'm going to leave this as a kind of an exercise for you at the moment. But if you're interested in what is sine of 2 theta, put a theta here and a theta here. 2 theta, theta plus theta. And you get sine theta cosine theta plus sine cosine theta sine theta. So 2 sine theta cosine theta. Okay, and again, check that. Do some work. And then cosine of 2 theta, use a theta here and a theta here, or angle, whatever it is, 2x, use an x here and an x here. And that's the trick for that. And if you're interested further, how do you find, for example, sine of half an angle, or cosine half an angle, I recommend when you get cosine of 2 of the angles, so cosine 2x, use the 2x as 1, like a theta, and then everything else will be using a, so if this is, for example, cosine of a theta, you'll eventually have theta over 2. So compare with the double angle to theta with the single angle theta. So again, I'm going to leave that as an exercise for you, and actually we'll do that next time. Okay. So thank you so much for having me, and y'all have a great day. And I will continue with the double and half angle formulas later.